So today we'll be looking at section 6.2 from your Sullivan book. The title of the section in the book is One-to-One Functions, Inverse Functions. Our objective for today is that I can determine whether a function is one-to-one and find the inverse of a function. I can obtain the graph of the inverse function with the graph of the from the graph of the function. And all of that hopefully sounds familiar to you because it is something we've covered in previous units, but today we just wanted to do a quick review and use it kind of as a foundation to build on for the rest of this unit. So if you need to at any time in the video, I suggest you kind of just pause it so you can copy down what you need to, but I'm going to try to go through this pretty quickly since majority of it is review. So just to kind of open up, you do not need to write this down. It says a function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. So one-to-one is what it sounds like. One x goes to one y, or one input goes to one output, and vice versa. Really just kind of what you're looking for at one-to-one is no repeats in your inputs and no repeats in your outputs. So I'm going to show you guys some examples really quickly from page 411 in the Sullivan book. Don't really feel like you need to write these down either into your notes. I just wanted to give you kind of some visual examples of what it would look like for one-to-one. So again, page 411 in your textbook. And of course the answers are there also. But I just wanted to show you a little bit here. It says determine whether the following functions are one-to-one. For the following function, the domain represents the age of 5 males and the range represents their HDL or good cholesterol level. You'll notice here I have this would be more called a mapping of an input to an output. Here we have a list of ages, here we have cholesterol levels. What I want you to notice here is that there are two ages, age 55 and 61, that both have a cholesterol level of 38. So if we were to decide if this mapping is one-to-one or not, we would say no, because there's this piece here where there's 2-to-1. So in order to be one-to-one, each one of these ages would have to go to its own cholesterol level. And then if you look at part B, the list of points, -26, -13, 02, 15, 28. I would just kind of scan through to see if this is one-to-one or not. I see a -2. I don't see any other x values of -2. A -1, no other x values of -1. I would just kind of go through like that, making sure I don't see any x values that show up more than once or any y values that show up more than once. So this function is one-to-one because there are no two distinct inputs that correspond to the same output. So those would just be some quick examples that you can visually kind of see what the difference between one-to-one and not one-to-one would be. Also a reminder of something we spoke about in our last unit when we were talking about the inverse. We were talking about the horizontal line test. So if you feel like you need to, you're welcome to write that down again. We talked about if every horizontal line intersects the graph of a function f in at most one point, then f is one-to-one. So I reviewed with you that day that there is a vertical line test, and that's to tell if something is a function or not. The horizontal line test tells if something is one-to-one. And what we talked about was that if it passes the horizontal line test, not only is it one-to-one, but we know that the inverse of the function also passes the function test. So we're just going to take a look at an example, and this is what you can start writing down on your paper for your notes. We're going to take a look at just a couple quick parent graphs and try to determine if the function is one-to-one or not. So our first function is f of x equals x squared. So I'm just going to sketch for you the parent graph. What you could also do is get out your little yellow booklet of parent graphs and just maybe take a look at it there. So just give me a moment to graph this for you real quick. Some of the points we have for our parent function of x squared are 0, 0, 1, 1, 2, 4. And then there's symmetry. And I can sketch that in. All right, so if I were to do the horizontal line test, since we're using the graph to determine if it's 1 to 1. If I were to draw a horizontal line, and even if I just were to lay my pen down horizontally across the graph, hopefully you would notice it does hit in more than one spot. It looks like it would cross the graph in 2 places. So I would say that this graph is not 1 to 1. And that was really the only question we were answering. If you remember back to when we were graphing inverses, the inverse of this is that sideways parabola, which we talked about how it is not a function itself. F of x equals x squared is a function because it passes the vertical line test, but it is not 1 to 1 because it does not pass the horizontal line test. So we have different uses for those 2 tests. And then one more graph we can take a look at. Letter B is the cubic. So again, if you want to take a look in your little yellow booklet, you would see what the graph of this looks like. But if I just quickly sketch it, just enough so that I can do the test. Some of the key points on a cubic graph are 0, 0, 1, 1, 2 would take me all the way up to 8, -1, -1, and then -2 would be down at -8. So just kind of a reminder that you get this curve. And if you take a look at this graph and try and do the horizontal line test, again, even if I just set my pen down horizontally, you'll notice that everywhere on the graph it would only cross in one place. So I would say that this does pass the test and is 1 to 1. And you could write g of x is 1 to 1 to be more specific. Okay, so just kind of a quick test of some graphs. Next we're going to look at an example where we kind of just take a look at some points and find their inverse. So just a reminder of how to actually find the inverse. All right, so again, just kind of the first thing we're looking at is deciding about 1 to 1. Now we're going to move on to talk about inverse. And again, all of this is the same as when we did it before, just a quick review. All right, so I didn't give this example an example number because I thought maybe we could just talk about it, or I can write a answer for you here and you can just take a look at it. I don't know if it's really necessary to write it down since we have covered this before. So it says to find the inverse of the following 1 to 1 function. Remember we talked about finding an inverse and just doing a switch between an input and output, and in this case that would be an x and a y value. So my inverse would simply just come from taking my x and y values of my points and switching them. So this would be -27, -3, -8, -2. -1, -1 would look the same. 0, 0 would look the same. 1, 1 would look the same. But then I would get 8, 2 and 27, 3. And I don't know if you can tell right away from looking at those points, but those are the points that we would get for that cubic graph, the x cubed. So this would be the inverse of the points for that graph. And if you remember when we were talking about inverses before, we noticed that if the x and y values were the same, that point actually did not move. So you'll see that here as well. So just a quick reminder of what we can do to find an inverse just by switching our inputs and outputs, or in this case, x and y. Here's something I really want to make sure you do please write into your notes. So there's 3 little stars or bullet points here. So maybe just pause the video so you can write those down. I'll give you just a minute while I fold my paper. Let me read over it with you, and then I'm going to go ahead and move on. We'll see the application of it in our following examples. It says if f is 1 to 1, it has an inverse function, and the notation we're going to use is f, it looks like to the -1 power. That's the inverse notation. So if it's 1 to 1, we know it has an inverse. The domain of our original function becomes the range of the inverse, and then the range of the function becomes the domain of the inverse. And again, that's because of the switch or the flip between our input and output, which is usually our x and y. And then something else that we learned in the last section we did on inverses was if I take the inverse of the function, I should just get x, and f of the inverse should just give me x. Before we saw these connected as f of g or g of f, so now we're seeing the inverse notation. But again, the check that we did to see if something was an inverse or not was that their compositions had to equal x. So example 2, and this is one that I would want you to include in your notes, is just verifying that these two equations or functions are in fact inverses of each other. So it doesn't matter which kind of composition you start with, but if I do g of g inverse, it means that I replace the x in g with this entire expression of g inverse of x. So instead of 2 times x, I would get 2 times 1/2 x minus 3, and then the plus 3. So what I've written in this parenthesis here is the g inverse of x equation, and it's taking the place of the x in g. What this would look like if I simplified it, careful, don't distribute multiple times here. If you want to distribute the 1/2 through, you can, and then multiply by 2. But if you just start by multiplying the 2 times 1/2, that would simplify out, and I would just get the x minus 3 and then the plus 3 here. And it looks like I just get x, which is what I was hoping for. Then if I test the other, g inverse of g of x, what's happening here is you're taking the 2x plus 3, that entire equation, and substituting it into the x in the inverse equation. So it would be 1/2, and instead of x minus 3, it's 2x plus 3, and then minus 3. So if I simplify that, 1/2 times, looks like that would just be 2x, and 1/2 times 2x would just be x. So it looks like it works out. And because it just says to verify, I don't feel like we need to maybe make a summary sentence there as long as we're showing our work to support it. So one thing you might be asked to do in the assignment related to this is verify that two functions are in fact inverses. Something also, just as a reminder, it's not something you need to write down because we talked about it before. The graph of a function f and the graph of its inverse, and the notation again looks like f to the -1, are symmetric with respect to the line y equals x. So remember, that's that identity line. It's the line that goes through the origin and has a slope of 1. We talked about not needing to graph it, but you could, and it helps you see how the inverse and the function are symmetric to each other. Also, just a reminder, and this is a spot where you might want to write this down, because I talked to you guys about it before, that these are steps for some reason that I see students forget all the time. So not only are we going to look at graphs of inverses, but also how to find the equation of an inverse. So step 1 would be to interchange x and y. So that would kind of be the main thing. Hopefully this notation here and here doesn't kind of throw you off. Just here in the middle, switch x and y, and then solve for y. There's some notation in there to make it a little bit more official, but that's what we're doing. Switch x and y, and then solve for y. All right, so I'd like to try to squeeze in 2 more questions with you, example 3 and 4, where we actually practice what we just talked about. So here I'm given a function, f of x equals 2x plus 1 over x minus 1. The restriction here that x cannot equal 1 is because it would make our denominator 0 and the function undefined. So we're supposed to find its inverse, the domain and range. It doesn't say that we need to graph. So I would start by finding the inverse, maybe just writing on my paper what the function is that we're starting with, since I don't have that on my paper yet. Alright, then I'm going to go through the steps. So the first step was to switch x and y, and this would be 2y plus 1 over y minus 1. And I know that this looks a little different than maybe what we've seen before because there's a y in 2 different places. So here's my suggestion for solving for y. Multiply both sides of your equation by y minus 1. Here I would get xy minus x equals 2y plus 1. And again, maybe it doesn't look all that great yet because you're noticing there's a y in two different places of the equation. So my suggestion is get the y's together on one side of the equation and the non-y's together on the other. So see if this makes sense to you. xy, I'm going to subtract 2y from both sides, but I'm going to add the x to both sides. So the x has been added, the 2y has been subtracted. Still doesn't look great because I see a y in two places, so I'm actually going to factor the y out, and it would be x minus 2 and then x plus 1. Last step would be to divide by x minus 2 on both sides, and I would get y equals x plus 1 over x minus 2. Last thing would be just to please use the correct notation. This would be f inverse of x, so x plus 1 over x minus 2. Last thing we have to do is to find domain and range, and the easiest way to do this is to really just find the domain of f and the domain of the inverse, because they're connected to the range of each one. So what I like to do is kind of set it up like this. I have domain and range for f and for f inverse. So if I want to find the domain of f, take a look at the function. We know that our issue when we have an x in a denominator is that we don't want our denominator to equal 0. So what makes my denominator equal 0 would be positive 1. So I would say x cannot equal 1. Now we know when we find an inverse, what we're doing is switching or flipping our x and y. So what happens is our domain and range flip also. So if the domain of my function f is x cannot equal 1, the range of my inverse is y cannot equal 1. And there really wouldn't be a way for us to be sure of that unless we graphed and saw it. So making that connection is going to be really helpful. Again, it's because our x and y's flip with each other when we go from function to inverse. So our domain and range would do the same. Just please be careful, don't put an x here and an x here. Range should be represented with a y. And then easiest way to find the range of f is to start with the domain of the inverse. So if I look here at my equation of my inverse, I have an x minus 2 in the denominator. Looks like x cannot equal positive 2 because it would make my denominator 0. So this is x cannot equal 2, which means here y cannot equal 2. So again, just maybe write yourself a little note or make sure you see that there's a connection between the domain of one to the range of the other. Again, it's just because there's a flip or a switch between our x's and y's. Okay, and then our last example is to actually graph on top of what we just did. So finding the inverse, but also practicing the graph. All right, so last example, example 4. We're told that f is 1 to 1. We're asked to find its inverse, state the domain and range of f and its inverse, and then to graph f and its inverse, and y equals x on the same coordinate axes. So the graph's going to look maybe a little bit overwhelming. Let's start with the function. To find the inverse, I would replace x and y, so x equals 4 over y plus 2. I would work on solving for y the same way we did in the last question. Multiply by y plus 2 on both sides. Xy plus 2x equals 4. In this case, there's not a y in two places, so it might be a little bit easier. I would subtract 2x from both sides. Xy equals 4 minus 2x, and then divide both sides by x. So y equals 4 minus 2x over x. And you can leave it like that, or if you'd like, you can write it as 4 over x minus 2x over x and do some simplifying. But I feel like most of you would prefer to stop as soon as possible, and this would be the spot. All right, so I found the inverse. If I wanted to talk about domain and range like we did in the last question, I'd set up my paper domain, range for f, for the inverse. The domain for f, if you look at the denominator, it says x plus 2, so the value I would have to exclude is x equals negative 2 because it would cause my denominator to be 0. So x cannot equal negative 2. And try to remember that the domain of f will also match up with the range of the inverse, but just make sure you use a y. Domains are easier to find than ranges. Ranges, you would probably need the graph, so I would suggest you find the range of each, not the, the domain of each, and then use those to find the range instead of trying to use the graph. For f inverse, it looks like the denominator is x, so what would make that 0 is 0. I'll have to exclude 0, which means I exclude it from the range here. Okay, next thing is the graph, and in order to be successful with this graph, you have to remember some things about the graphing the reciprocal function, which it's been a little while, so I'm not sure how much you guys remember. So if I think about graphing f of x, my original function, this would be the reciprocal graph shifted to the left 2, because the plus 2 is in the denominator. It means I would have a vertical asymptote when x equals negative 2, which makes sense since I said in my domain that x cannot equal negative 2. So hopefully that would make sense that there would be a vertical asymptote there. For my range of f down here, I did say that y cannot equal 0. That would be the same thing as my x-axis. So you can draw your asymptote, but you're not going to really be able to see it. And then I would make a table just to find a couple extra points, so I would have some points to plot on my graph. I would try a point 1 to the right and 1 to the left of my vertical asymptote. So if I substitute in negative 1 here, negative 1 plus 2 is 1. I get 4 over 1, which is 4. And then if I try, let's see, negative 3, so it's on the left of my vertical asymptote, I get 4 over negative 1, which is negative 4. 1, 2, 3, 4. And 1, 2, 3. So just remember that it means you would have some kind of curve like this. And if you don't remember anything about the reciprocal function, I would look up your parent graphs on reciprocal function. And then if I wanted to graph the inverse, so I don't know if you want to make a note to yourself, which would be helpful. This is f, this is f. To graph the inverse, I would again just kind of flip my x's and y's. I'd also have to flip my asymptotes. So instead of having an asymptote at y equals 0, now I have an asymptote at x equals 0, which would be, and maybe I can use, I guess, just a highlighter to graph this one. Let me see, maybe orange would be better. Maybe you can kind of be able to see them to compare them. And then my horizontal asymptote, if you look at our range for the inverse, was y equals negative 2. So that would be here. And instead of actually trying to graph my inverse from scratch, I would take the points from my original function and just switch the x and y like we had done before. So it looks like I have a point at negative 1, 4. So I would now have a point at 4, negative 1. 1, 2, 3, 4, negative 1. And now I would also have a point, instead of negative 3, negative 4, it'd be at negative 4, negative 3. 1, 2, 3, 4. 1, 2, 3. So it should look, and just try to be careful here. Let's see. I know that this is going to come up this way, and this is going to come through this way. Honestly, this graph is kind of on the difficult side because there's so much happening in one graph where you have multiple asymptotes. The last thing they did ask us to do was to graph the line y equals x. And if it's just going to look like a big mess to you, I'm okay with you maybe not doing that part on this particular problem. But I'll use a different color and maybe that'll help you guys see it. This is supposed to represent the symmetry, and again, there's so much going on here that it probably doesn't look that great. But if I turn it, maybe you can see it, I'm not sure, that there's that symmetry between kind of the curve I did in pen and the curve I did in orange highlighter. And the same thing here, here, and here. And they're not the best looking graphs because I didn't find a lot of extra points. I only